All right, so the only thing I want to say would be we got 2 more lectures, will be today and also Wednesday, and we got 1 more tutorial, the last one this Thursday. So these will be the 3 sessions last. So for our session last Wednesday, which was converted to office hour, no additional lecture to study, so don't worry. I want to balance it out with some lecture video I posted to you guys, which was longer than usual. Hopefully things will balance out. But we do have to cover some important topics today, for sure. So I want to finish off the Kruskal's minimum spanning tree algorithm, especially the cut property, which will help us justify the correctness of the algorithm. So I'm going to give you the intuition, and there'll be a little exercise I want you to really try. That will be just follow through the slides bullet point, and then I got some solution for you as well. And then hopefully in the second half, we can start about dynamic programming. You may have heard about the topic. It's actually quite a fun topic. It has a very nice complementary feature to recursion, which is something we'll do. I'll try to do at least 2 to 3 examples together with you today and also Wednesday and also tutorial. I can even give you some example question, like an exam style, in which case you can also practice. We can go over them too before the exam, okay? All right, so I want to do just one very quick recap from last Wednesday, okay? So this is the Kruskal's algorithm. I'm going to dive a little bit deeper into it just to justify why it's actually considered as a greedy algorithm. We're going to do a similar justification, which is warm them up, just to remind ourselves the steps. And of course, today I'm making the assumption that you guys know how to compute the minimum spanning tree. If you haven't really caught up the lecture from last Wednesday, you may want to do it soon. Otherwise, you will easily get lost about the cut property, which we're going to talk about today. Okay. All right, so make sure you follow this example here. This example corresponds to just slide number 85 on the slides, okay? And then this table here, you can think about it's more like a predefined version of what we did in the lecture. So that one there is something, when you do the exercise, I'm going to assign to you at the end of the minimum spanning tree lecture. You would just have to look at the trace table and see how you can see the corresponding parts in the bullet points about cut property and also the Kruskal algorithm correctness. That's something I will mention to you at the end. All right, so for today, I want to start with just very quickly to go over this version of the Kruskal's algorithm. We haven't really gone through the pseudocode of the Kruskal algorithm. We just kind of did the example right away to do tracing. But I think now you guys have some idea about how it should work. Okay, let's now take a look at this and then try to review it and see why it's a greedy algorithm, right? Greedy steps. And we're going to mention about the 4 different criteria that a greedy algorithm should really satisfy. Okay, we can easily see them. Okay, we'll talk about also running time at the end. So first of all, let's now see that we have a loop over here, right here. Right? You can see that this is a loop. Okay. So we are actually going to do a step-by-step construction of some final solution, which will be the spanning tree, right? Okay, so this one is a little bit different from Dijkstra algorithm, in which case we are trying to compute the shortest path. Okay, so number 1, it is a step-by-step construction. So step-by-step construction of some ultimate solution. And the solution we are trying to construct is the T, right? If you remember in the tracing table, we try to show you the T, how it's actually growing from iteration to iteration. Every time we're just adding some tree edge whenever we see one. Okay. So here will be the T, and will be the set of edges of some spanning tree, minimum spanning tree to be more precise. So edges in some minimum spanning tree, right? Not only just spanning tree, but also the weights will be the minimum for the summation. And then criteria number 2, we want to see that for every iteration, for every step, we have feasible choices for us to choose. But we're going to choose the one that's going to be the cheapest according to some cost function. Okay. So what we'll do is we're going to look at this line here. Okay. So that line there, first of all, we have the choices, which will be in the priority queue. So the queue here, whatever that remains there, represent all the choices we have. Okay, so that'll be criteria number 2. So we got multiple feasible choices. So there are candidates to see how we can expand the spanning tree. Feasible choices that exist to extend the capital T that we're trying to build. And the choices we are talking about, unlike vertices in the case of Dijkstra algorithm, we got edges to consider. Right? So these will be the edges that remain in the priority queue. That remain in the priority queue. Right? Criteria number 2. And criteria number 3. So we have to take a greedy step to, according to the cost function, in this case, it will be the weights of the edge, which simply choose the minimum one, which will be top of the heap. Once we choose the edge, that will be the greedy step. And then we try to do things that follow. So this one here will be how we extract the minimum from the heap. Okay? So this will be the crucial, let me just draw better. This will be the crucial greedy step. Okay? So this will be number 3. Greedy step. And then we want to choose the minimum edge, which you want to choose the edge with the minimum weights. U and V. Okay? And the way we choose it is according to some cost function. And the cost will be just according to the weights. So whenever you're given an edge, we want to know what's the corresponding weights. So that's the cost function. Okay? So the cost function that we have will be the weights of any given edge. And each edge will be the origin and destination vertices. And specifically for this greedy step, which we'll dive deeper just after a few moments. In order for us to justify about the Kruskal's algorithm correctness, somehow it's iterative, so we have to think about what's the looping variance, in which case I also give you some intuition. There is a so-called cut property, which we also have to go deeper, go thoroughly. The cut property allows the greedy step over here to be justified. Let me mention the name over here, but you're going to see when you study to see how it can be linked back to the pseudocode. So the greedy step is about choosing some minimum edge. Also the so-called cut property, C-U-T, okay, cut. Ensures that we are on the right track. T-R-A-C-K of building a minimum spanning tree. For every greedy step we are taking, we're always choosing the minimum edge. And the cut property tells us as long as you keep choosing the minimum weight edge, you're really trying to build minimum spanning tree, starting from size 1 all the way to size capital V, the size of the vertices minus 1. Right? We're just building it to be larger and larger. But the cut property is something I will state to you and also give you some visualization to see. Okay? And the exercise I want you guys to try at the end of this lecture is to go over some bullet point in the slide that's very textual, right? Very a little bit mathematical, very formal. I want you to, based on the intuition we talk in the lecture, go over those points and look at the tracing table. Are you able to find out maybe some examples from there? Okay, that's something I want you to try. And there's also some exercise video optional. If you want to take a look, feel free. Okay. But it should be quite straightforward once we talk about intuition at the end. All right, that's number 3 about greedy step. Finally, the greedy step, also the spirit is once you make that choice, you never undo it. You commit to it. Okay. So as soon as we have got the minimum edge, minimum weight edge chosen, this will be number 4. We never put it back to the queue. Like in the Dijkstra algorithm, once we have processed the vertex, we never put it back to the priority queue, just remove it. Okay? So that'll be number 4. Once removed and processed. And I will talk about this processing part very quickly, okay? In just one moment. I'll get there. And processed. never put it back to the priority queue. And let's zoom in a little bit. Okay, I'll help you a bit. So this part here is about how we do the processing for every greedy step over here. All right, over here. I'll draw some correspondence back to the tracing table from last time. So hopefully that will help. Okay, so we are talking about process, right? So I'm talking about right here. Okay. Basically, we have to, given the UV, which will be the edge with the minimum weights, origin and destination. Given the origin, given the destination, find out the corresponding clusters. That'll be the first step. How do we see that? For example, let's go back to last time, right? For example, let's see here, the minimum weight edge we find was AB. So what we do is find out what's the corresponding cluster containing A. What's the corresponding cluster containing B, right? So that's the operation. Exactly how we implement this, I'll get there when we talk about time complexity. But for now, just remember the correspondence. Okay, let's go back. And the next line. And then we're saying if the two clusters for U and V, if they're different, that means we have to use that edge we just extracted from the heap to join them, to cross them in some way, right? So this is where if you got this not equal to, this one tells you that UV is a tree edge. Okay, let me show you again the correspondence. We got many examples from there. Let's say for this one here. If you look at this one here, we have extracted A and D, right? That's a current minimum edge. A belongs to this cluster. D belongs to this cluster. These two clusters are different. That's why we have to merge them. So the way to merge them conceptually is simply collapse the set into A, B, C, and also D into the same cluster. Exactly how we do it, bear with me. We'll talk about it. It's actually quite an intuitive implementation, okay, when we talk about time complexity. And of course, let's say if we have chosen something that's really have the origin destination, but they belong to the same cluster. In that case, there's no merge to be done because that's conditional, right? Very important for you to remember this part over here is conditional. We only do the merge if the two vertices belong to different cluster. That's really for us to merge and then to join them, okay, or cross them, okay? And then we try to merge them as well. So we somehow got different operations related to the cluster. That's something we have to introduce a very simple ADT called partition. But I'll talk about it a little bit later after the cut property, okay? Right, as you can see, the Kruskal algorithm itself is not very complicated. It's actually very straightforward about what you should really do, especially after we did a complete example last time. At least get yourself familiar with this. And then let's now talk about something a little bit deeper, about some formal terms, okay? Just to see how we can go on our way to really justify. Okay, let me just say one more thing. So after each greedy step, the solution so far is still partial, which means the number of edges in capital T may not be reaching the number of vertices minus 1 just yet. So that's why it's partial. But at least we know we are on the right track. Partial in the sense that T is still subject to extension. Okay, extension. Okay, important to know it's still partial, but subject to extension. If you go back to the tracing table right here, think about this is partial. Sorry. This is partial, this is also partial, all partial until we get to the end of the last iteration is complete solution, right? Everything before that will be partial solution until we get to this equation, right? The number of vertices should be number of vertices minus 1. Okay. All right, any questions so far about Kruskal, right? This is not difficult, just to go over the pseudocode and also which is based on, which is how our tracing was based on last Wednesday. Right, so now let's go a little bit deeper. Okay, it could be a little bit dry, but I'll try to make it intuitive, but shouldn't take too long, right? But I think the important part is for you to do that exercise. Okay, so we are going to clarify 3 terms: partition, cluster, and also cut. Okay, let's now first of all talk about partition and cluster. So these two are rather corresponding to what we said last time. Cut will go a little bit beyond that, just make it a little bit more general. But let's talk about partition and cluster first. You guys can read the slides, but I'm just going to use the tracing table and show you example. That'll be the best way. Okay, so there's a tracing table on the slides. And then let's now start with partition first. A partition is simply a set where each member is a set of vertices. Okay, and I'll look at example very soon. So let's write it down. Partition is a set where each member is a set of vertices. Okay, so it's a set of sets. It's a set where its member is also a set of vertices. Let's see example right away, especially let's compare this extreme. When we first start with, we got this partition right here. Let me make it a bit thicker. So this is the initial partition we have. And this is the final partition we have. In the initial partition, every vertex belongs to its own cluster. So every vertex belongs to its own connected component. They are not really connected yet by any tree or internal edges just yet. Okay, so initial configuration is such that initial partition. Each vertex in its own cluster. And of course, you can also think about each cluster really correspond to some connected components that we are trying to, we want to really reduce the number of connected components from the maximum down to 1. That's what we want to do. Okay? And of course, the other extreme would be after the final iteration. Okay? This will be the final partition. This will be the final partition, where all the vertices are in the same cluster or connected components. All the vertices belong to the same single connected component. That's where we got a spanning tree. All right, that's about partition. The next one will be about cluster. Okay, so the cluster over here. Cluster itself is a set of vertices. A set of vertices. Okay, and then, you can think about, and a cluster is simply a member in a partition. I'm just talking about the concept bidirectionally, but you can see that they just confirm each other. A cluster is a member in some partition. All right, so in the initial partition, you can see we got a cluster. 1, 2, 3, 4, 5, 6, 7, and 8. And then in the final partition, we got just one single cluster, right? Partition versus cluster. And let's try to compare how the clusters evolve as we go for iteration. That's also very important. Let's choose vertex A, okay? So the notation, let's think about the notation here. Because in the pseudocode, let me just switch quickly. In the pseudocode, you can see that given some vertex, we say C of U and C of V. What does that really mean? So if you're given a vertex, I want to find out what's the corresponding cluster containing it. That cluster might contain more than just that vertex, maybe other vertices as well, right? So let's now see the notation, and I'll show you some observation. Let me choose vertex A. So here, if I say capital C of A, this will be the cluster containing vertex A. You will see that in this particular run, C of A is just going to strictly grow between iterations. But let's verify that. You can see in the initial configuration, this is the cluster containing A, C of A, right before the first iteration. And then at the end of the first iteration, after we have connected A and B, right? That's the minimum edge we chose as a tree edge. After that, we have a larger cluster because we have chosen to merge these two, right? So now it's a strictly larger cluster. So at this point, if I ask you what's C of A, it will be this cluster, C of A. So the capital C of A, the cluster containing A, depends on the timing of the tracing. It could be different. That's the main idea I want to show to you. Right? Let's do one more. And then in the third iteration, we try to grow that cluster even further by connecting B and C. So now we got an even larger connected component or cluster containing A, B, and C. So over here, you can think about C of A is even larger. Right? All right. So let's now make this point. So to evolve from here to here, and to evolve from here to here, okay, let me write it here. So we are saying the connected component or cluster containing A will simply grow throughout the iterations. And the way to grow it is by having an edge, the minimum weight edge, to connect the clusters. Okay? Connected components containing A grows through merging. And the way we do the merge is by tree edges. Via tree edges. Okay? We're basically just trying to look at the same tracing for the second pass. But now our focus is not just about step-by-step tracing. We're trying to observe between iteration. What's the observation we can really infer from there? Okay? All right, let's look at one more example, and then we can move on to talk about the cut. Okay? Let's look at this one here. Okay? I just want to show you some equality here. So here, if I choose, let's say, A and B, you can see A and B, they are in the same cluster. I'll make it larger. I'm talking about this particular partition. You can see that A, B, C, D make this particular cluster. So A and B belong to the same cluster. So that's why we can say the C of A is equal to the C of B. They represent the same set of vertices. And let's choose some counter example which will make the equality false. For example, I can choose maybe F over here, and let's say H over here, right? By choosing these two, I can say the cluster containing F not equal to the cluster containing H. You can make other example too, right? Just remember the way we compare the cluster is to see if they're disjoint. But it turns out to really implement this disjoint, it can be quite cheap, just constant operation. I'll show it to you. Okay. All right, I think that's about it. I want to say about partition and also cluster, right? Cluster, set of vertices, partition, add one more set as a layer. Okay, let's get to cut. Okay. The cut here could be slightly confusing because, okay, let me just talk about it first, and then we'll see. May not be too bad. So we'll talk about cut. Okay. Once we talk about the definition for the cut and see some example, we'll state the cut property and see how that can be related to the correctness for Kruskal. Okay. So think about cut as a way. So a cut is a way to view the partition by two sets of vertices. Okay, for example, if you look at right here, this is my partition. And here I'm looking at one set of vertices and then the other set of vertices. That one happened to correspond to cluster idea. However, the confusing bit about the cut is it doesn't necessarily correspond to exactly two cluster, not necessarily. That's a problem, right? But this one here happened to be a cut. That's okay because we got exactly two cluster. What about, let's say, for example, in this one here, right? This one here, I can say I consider this set only, which consists of just A, and then the rest as another set. That's how I view a cut. Fix one set of vertices first, and then the other set is simply the difference. Okay, I'll write it down. All right, so we have two cases. Okay, I'll show you both cases. So based on this definition here, so we got two cases. Case number one, you might have exactly just two clusters. That might be just an easy example for you to see right away, to see exactly two sets. But in general, it could be one cluster or one set and then the rest. It could be just one cluster, for example, versus the set of remaining vertices. Okay, so we got two cases. Okay, this will be case number one, and this will be case number two, okay, which will be pink. Okay, case number two. Okay, I'll give you one example each. Okay, let's start with case number one. Again, it's just easier to think about. Somehow the partition, you got only two sets, right? Exactly two. So let's now take a look at right here. Let's look at this partition. Okay, and this partition here. So think about, this is the first set, and this is the second set. Okay. One thing I think might be useful, when you actually study for this cut idea, the formal definition, which is 100% precise, is about here. Okay. So let's say given a partition, you kind of choose a set of vertices that's capital S, and then the rest, which will be the whole partition, all the vertices set minus S, just the rest of the vertices, right? That's how you actually divide the partition into exactly two sets, okay? But I'll show to you exactly how to see that, okay? So given this particular partition over here, right? So what we're doing is, and then we actually have this edge, right? Remember this beginning of iteration number 9, this is what we have. And then we want to do something about it. And what we did in iteration number 9 is to use the tree edge right over here to connect the two, right? So let me just write it down here. So this is what we chose as the tree edge for that particular iteration. And then let's now write down the cut. So the cut that we have is, we have our partition right here. And then we're going to split that into exactly two sets, okay? Now in this case, we have the first set, A, B, C, D, E, F, G. Okay, let me move that around slightly. Okay. So think about this one here is the capital S. Right? Again, if you go back to the slides, that's the capital S you will see right here. And then the other one is simply the rest. We know that we got A, B, C, D, E, F, G. What's really left is H. And then we got just H. Okay, so think about this second set over here is the set of all vertices set minus capital S. So just remember, whenever you want to discuss a cut, given the partition, choose S first and put the rest into the second set. And the second set there might contain several clusters. So cut is not exactly the same as like a cluster, right? That's the main thing you want to understand. All right, one more thing to say. And then, in this case, we are trying to choose the edge, E and also H, right? That's the edge. So E is here, and H is over here. Given a cut, we got S and also the rest. If we are trying to build an edge between them, we say that this edge crosses it. Okay, so this is the EH. So what we say is H, EH crosses the cut. Let me recap, okay? Whenever you're given a partition, choose a set. In this case, let's say we choose a blue one. And then the remaining part will be just put into the other set. So now we've got two sets exactly, this and this. And if we are trying to choose the edge, that will go across these two sets. In this case, E belongs to this set here, H belongs to this different set here. So we say that this edge crosses the cut. All right? So this is like a case number one, where the two sets just correspond to two clusters. But let's see, it doesn't really have to. Let's do one more example. Okay? The second example there is going to be more general you want to think of. Okay? So let's say I would choose this beginning partition, just this one. Maybe not that one. Let me see. There we go. This one. I think this one's good. All right, let's say this one here. And as you can see, the edge that we are trying to add for iteration number 6 is D and E. So D is here, and E is over here. So now how do we view the cut? D, the origin, belongs to the cluster ABCD. So that'll be the first set. Let's fix that. Right here. And for E here, don't think about the E simply just belong to this particular cluster. That's not the way to think about cut. Think about E simply belongs to everything else, just the rest. So I'm just going to put the green to contain all the rest. So now we got two sets, A, B, C, D in one set, E, F, G, H in the other set. That's the cut, two sets. Okay? I'll write it down, and then I'll do one more diagram to show to you. And then we can state the cut property. So you can think about what's going on here is we have a cut. So the cut that we have is we have a partition, and then we got two sets. A, B, C, D is the first set. A, B, C, D. And then The second set will be the rest, everything else, which will be E, F, G, H. E, F, G, and H, right? So we got exactly these two sets. Number 1 and also number 2. Okay, 2 sets. And the tree edge that we are trying to add to the T is DE. D and E. So think about D here and also E over here. So the edge, DE, we say that it crosses the cut. All right, just another example for the cut. Just remember, you gotta choose 2 sets that are disjoint from the partition. For this one specifically, let me draw one more diagram. Hopefully that might help further, okay? Let's say for this one specifically, number 6, okay? Okay, I'll put it on the top. Let's say this is the entire vertices, capital V. And then we are dividing that into 2 disjoint sets. Set number 1, we got A, B, C, D. We got A, B, C, D. And this set over here happened to be the cluster of D. Because you can see that D is right here. So that's a cluster of D. Right? That's the first set. And then the rest, we simply say just anything but A, B, C, D in the capital V. So the rest will be E, F, G, H. E, F, G, H. As you can see in the actual partition, E, F, G, H, they don't really belong to the same cluster. So the way I'm going to draw it, let me use dashed line just to say they just belong to a set conceptually. So it's simply just a set right here. And you can think about this set over here is simply all the vertices set minus the cluster of D. All right? I'm being very precise here. You can definitely review the notation a little bit later, right? Just to convince yourself what's going on. And then, finally, the edge that we are trying to add in this iteration, D and E. So we got D here, and also we got E here. So what we're doing here is we are trying to connect these 2 sets using that edge. So we're saying that the edge crosses the cut. So we got D and E. So essentially, this edge over here, which will connect D and E, we are really connecting this set over here and also this set over here. That's what we're doing. It's called a cut, crossing the cut. So here, let me just say here. So edge, DE, crosses the cut. Okay. Any questions? All right, think about the definition, right? So I think it's rather precise. You just want to be precise about how to distinguish between partition, cluster, and cut, okay? Okay, I think we're exactly halfway. Why don't we take a short break? After the break, I will talk briefly about the cut property, and then we can talk about time complexity. We should be able to talk a little bit about dynamic programming today, I think, okay? Okay, let's now build on the definition we did, that we went over before the break. Let's now talk about something called the cut property right here. So that one is on slide number, let me just be sure the number, 88. Okay. But I just want to talk about the cut property. And then the rest of the slide 88 is about some bullet point to really see how we can use the cut property to informally justify. It's not exactly informally, it's like a semi-formal. Not exactly formal, but also not exactly informal, just semi-formal. To justify the correctness, that one there will be the exercise for you to go over the slide and make sure you understand. Okay? But I do have some resource there to also help you. Let's talk about the cut property, okay? Let's now talk about cut property. To start with, this is something you want to keep in mind. The cut property is something you don't have to prove. It's more like an axiom. You're simply given that. You don't need to prove it. It's given to you, right? Think about it's an axiom given to you. And the idea is the cut property is going to be asserted at the end of every iteration for the cruise-cut algorithm. Every time after we have added one edge into the capital T, the tree, we can apply the cut property every time, okay? Applicable to the end of each iteration when a tree edge is added. It's a very important insight, but I'll try to repeat it again. Once I draw the whole diagram, you will be able to see. Right? At the end of each iteration, when a tree edge is added. Okay, let's now see what we have. Again, imagine that this is our whole graph, the input. And the input is weighted and also connected. That's our input graph. We got V and E. Has weight on every edge, weighted, and also the graph also happen to be connected. If that's not connected, there's no way you can find a spanning tree, right? Because it's not even connected. All right, so let's now talk about any arbitrary iteration, right? So now we're talking about some iterations. For example, at the beginning of iteration number 6, we have a cut where we got one set, we got the other set, and then we have an edge that's going to cross the cut. That's what we said before the break with a concrete example. Let's now make it more general. So what we have is, we have capital S. Okay, so capital S has to be some non-empty set of edges. One example, by the way, the cut property is actually a very general property. It doesn't apply just to the cruise-cut algorithm, not just that. If you want to devise other minimum spanning tree related algorithm, you might still also use a cut property. But let's see. You can think about the capital S over here. Example, the capital T at the beginning of the iteration. Okay, think about that's what we already got so far. Okay, and then, you know what? Let me just erase this comment here. It's not exactly, I do apologize. Let me erase that. I'll get to the T a little bit later. Okay, it's not the appropriate timing to really mention that. Again, if you're ready to take notes, please erase it. Okay, and keep it simple. So we got two sets over here. Okay, we got set S, and then we got the rest. So think about the remaining vertices would just be capital V, all the vertices, set difference S. So we are basically saying this and also this, the two sets form a cut. So we have a cut. So the cut we have is, we have S and also the rest. Capital V, set difference, S. All right? It's a greedy algorithm, so we have some greedy step, meaning that we got multiple feasible choices. In order for me to reach out from S, I may reach out by one edge like this. I might reach out by another edge. I might reach out by another edge. I got multiple feasible choices. But I'm going to choose only one. That's the optimal. The optimal will be the cheapest one, right? So let me draw that. We might have some edge over here with certain weights. We might have another edge over here. Let me call this E. Let's say E happens to be the minimum weight among all the edges that can reach out. And we got maybe just another one, right? We can get multiple in general. So let's say here E is such that the weight of E is less than or equal to the weight of all other edges crossing the cut. If I pick this edge, it will be crossing the cut because simply reach out. And also, if I pick this one here, it can also cross the cut. However, I will pick this one. Why? Because that one there has the minimum edge, the minimum weights for the edge. I pick that one. There are so many edges I can choose to cross the cut, but I'll pick the minimum one with the weights. Okay? So this property here is also very important. All right? Okay, so it's going to reach out to this vertex here. Think about this vertex is not in S because we're reaching out. And also, it will be exactly a member of the other set, which will be the capital V set difference S. Right? Very basic set notation that will help us understand what's going on. Okay, we'll pick that one. So once we pick that one, with this will be the greedy step. Okay, which will be the minimum weights. Now here, so that will be the setup for the cut property. What's the actual thing we can say? The cut property tells you that once you have chosen E, guarantee the E itself will be a member of some minimum spanning tree. We don't know exactly what that minimum spanning tree might be, but we know there will be one that's going to contain E ultimately. Okay? I'll write it down, and then I'll show you why. Once we put this idea into iteration after iteration, it's very powerful. Okay? Okay, so greedy step over here. There is a minimum spanning tree. And notice that I say a minimum spanning tree. I don't care which one, as long as it will give me some minimum spanning tree. If you remember the tracing from last time, the minimum spanning tree we can get from the algorithm does not need to be unique. Sometimes if you got equal weight that happen to be the minimum, you can choose either one, right? So that's why it's not unique, not necessarily. Okay, a minimum spanning tree T such that the edge that we have chosen in the greedy step should be a member of T, that minimum spanning tree. Okay? And one more terminology, and then I will show you combine this cut property together with iteration, because greedy algorithm is iterative. And we say that this E we have chosen by the greedy step is so-called a safe edge. E is a safe edge. You can think about safe in the sense that we are still constructing our minimum spanning tree. We're not really trying to deviate our path by collecting the edges wrongly so that we don't have a minimum spanning tree anymore, ultimately. So it's a safe one. All right. Let's now try to just draw, also visualize the idea a little bit. Imagine that you got your tracing table. And we got iteration. For the Kruskal algorithm, for every iteration, the way we choose the minimum edge corresponds to exactly how the car property was set up, which means whatever edge we have chosen at the end of each iteration guarantee to be a member of some minimum spanning tree, guarantee, all right? So now after iteration number 1, and then we got the T. Let's say after this, we got E1 chosen. So that would mean E1 over here should be a member of some minimum spanning tree. So the whole thing would be some minimum spanning tree. I'll just say MST. So far, so good? So this is to say the very first edge we have chosen, that one guaranteed to be ultimately a member of some minimum spanning tree. That one's for sure, all right? And then, if we go for the second iteration, and now we got E2. It's more like a cumulative. So after we have added E2, we would have got E1 and also E2. E1 belongs to some minimum spanning tree. E2 as well. So both of them together will belong to some minimum spanning tree. Okay. That will also belong to some minimum spanning tree. And keep going. Once you get to, for example, the last iteration, and then you got this many edges. And the number of edges will be exactly the number of vertices minus 1. And we know that every edge along the way we have chosen at the end of each iteration belongs to some minimum spanning tree. So altogether, they should really form a minimum spanning tree. That's intuitively the idea. Okay. They also belong to some minimum spanning tree. We didn't really try to go for very formal into the proof. That could be too dry, but I think that that's the intuition. Number one, understand about how to state a car property. Number two, try to get some idea about how you can check the car property for every iteration. If you combine them together, because all the edges we have chosen will give us on the right track to get a minimum spanning tree. Once we collect exactly capital V minus 1, we get exactly a minimum spanning tree we want. Right? So of course, the car property is the critical one to rely on, but as an axiom, you don't need to prove. All right, think about it. You can definitely ask me a question a little bit later, okay? The exercise for you is to go over the rest of slide number 88 right here, and just to see how the car property can be understood maybe in different lines in the Kruskal algorithm. Okay, take a look at that, and then just in case it's needed, you can also, I will show you that, I just posted that. So there is a little exercise here, just about analyzing the car property in Kruskal algorithm, right? There's a video there. If you want to follow through, go ahead. But if you got any follow-up, you can also let me know, right? Kruskal algorithm. We didn't really do a very formal proof, but important to get the intuition. Okay. So there is one more topic about the Kruskal algorithm. I would say I'll skip it just for now, okay? That one is really about to figure out the running time. And in order to really derive the running time for the Kruskal algorithm, we'll need to learn about the little partition ADT. Let me do that either the beginning of Wednesday or maybe beginning of Thursday. I'm going to cover that, right? I think that's important. That wouldn't take too long, but I do want to spend about at least 20 minutes on dynamic programming. I think that's good for us to get some intro. Okay, I'll revisit about the time complexity for Kruskal Wednesday or Thursday, and then I'll leave the page empty just for now. Okay. And also, this will be the little exercise. You can, I'll show you that. So this will be the exercise. You can look at all the bullet points on slide number 88. I'll leave that clean for you, and you can do your own notes. Look at slide number 88. And then look at the corresponding part and see how you can find the corresponding part in the tracing table, okay, for the car property. Okay. All right. I'll revisit about the time complexity later. Let's now talk about dynamic programming. Okay, some idea. So there will be a new lecture slides. I already posted it. I think as of now, I only got 2 simple examples. I plan to do at least another 1 or 2. Okay, so you can expect this slide to be expanded in the coming few days, but I'll let you know. But let's talk about dynamic programming. Okay, we got 20 minutes. I think it's good intro. Okay. All right. Okay, dynamic programming. Number 1, you can think about dynamic programming itself. It's just like another design technique, just like a greedy algorithm. But of course, the spirits for the dynamic programming is very different from greedy algorithms. So you ought to know when should we really use dynamic programming. So there are 2 criteria which I will definitely go over with you, but I think the best way to go over them is by using some example. And the best example people usually want to use is the Fibonacci sequence computation. That's something I want to start with. Okay? So one is something called overlapping subproblems and also optimal substructure. So these 2, of course, wouldn't make too much sense right now, but that's something we're going to go over. And typically, your motivating scenario to apply dynamic programming is when you already implement a recursive algorithm, you find that it's too costly at the runtime. In that way, you might consider dynamic programming to somehow compute subproblem result in a way that you can keep reusing them. That's really the spirit about computing, store, and reuse. That's the spirit for dynamic programming. Oh, we'll get there. And also, whenever you want to do dynamic programming, you want to identify what's the so-called states. I'll talk about it. Base cases, recurrence relation is a formal name for recursive function or recursive method. That's really what I meant. Okay. Recursive function is something you learn in 2101, but we'll definitely review some example together. Okay. And now here comes the thing. So once you set up all the context and you also decided to really use dynamic programming, so there are 2 approaches. We're going to learn both. Both are valid. Okay. One is the so-called top-down approach. And for the top-down approach, we're still going to make it recursive. We're basically improving the recursive method that's not efficient by introducing an extra input parameter callback value. So we can refer to the result without having to recompute. I'll show you exactly. Okay? And by the way, this word over here is not memorization, it's memoization. Okay? I'll spell it out also together with you. Right? This is a common mistake too. Okay? It's a technique. The other approach is called bottom-up approach. That one there is not going to be recursive, it's going to be iterative. And to really make this work, you have to maintain so-called tabulation, like a table. And the table here can be 1D, like a single array, which is the case for, let's say, Fibonacci number. We can also make it 2D, and it's something I want to talk to you also maybe on Thursday in the tutorial session. You can also make it 3D, 4D, in general, in theory, but I think a 2D is the most complicated we're going to get to for this course. Okay, we're also going to talk about some running time. Dynamic programming can substantially reduce the running time. If somehow, after applying dynamic programming, you got everything to work, but somehow you do the analysis, the running time has not been improved. So that means dynamic programming is not that necessary. You don't really have to bother. You don't have to do dynamic programming for every recursive method. You don't have to. Only in those that will be applicable. Okay. All right, for slide number 3, 4, and 5, I got many texts over there for you to go over, but I would suggest we go to example right away. Okay? And then we'll see. Let's now revisit quickly about recursive method or recursive solution. Okay? Let's start from here first, and then I do want to mention some terms. Okay? Whenever you want to solve a problem there, and if you have an idea about, you may have some so-called base cases, which means the problem with very small sizes, which you can return the solution right away. Or you might have the problem with size just big enough. You cannot compute the solution right away. You have to somehow divide and conquer. So there are 2 cases. Okay? That's how you think recursively. Okay, so case number 1. You have a problem, and the size may be 0, 1, or 2, very small. You can solve it right away. So that'll be base case. versus the problem there may be big enough. You just cannot solve it right away. You have to divide them into strictly smaller problems. So this will be the recursive case. Okay, let's now go very quickly about divide and conquer. So think about, to go from here to here, we are basically dividing the original problem into strictly smaller subproblems. Divide. And then we kind of solve them individually. For this strictly smaller problem, I'm going to make a recursive call and get a solution. For this another strictly smaller subproblem, I'm going to make a recursive call and get a solution, and etc. Okay? And then the concur part is, once I get all these solutions to smaller problems, subproblems, I can now concur. By combining the solutions to strictly smaller problem, right? Let me recap. If the problem itself is small, base case, solve it right away. Don't bother with any recursive call. If the problem is too big, divide that into strictly smaller problems. For each one of them will be the input for separate recursive call. And then you got 1, 2, and 3, in this case, 3 separate solutions. And then for the ultimate solution, you just combine them somehow. Okay? So that's the overall picture for recursive method. That's basically what you were told, maybe in 2030 and 2101. But now we're going to see, for recursion, you might run into some bottleneck for running time. It can easily go to exponential, which means if your recursive method is simply trying to find out all the possibility, it could be 2 to the n. That's something we'll see in Fibonacci number, pretty much. Okay, so once you get a base case and recursive case at a runtime, usually you can build some recursion tree, which we'll try as well. So at a runtime, you will get some recursion tree. Runtime, recursion tree. Okay, let's now talk about 2 important ideas. Okay, number 1, if you look at the subproblem over here, you can say we say earlier, divide it into smaller subproblems over here, and we have to solve, in this case, all the 3 smaller subproblems. So we have to solve this one here, solve this one here, and solve this one here, right? Depending on how many subproblems we have, we're going to solve that many. Okay? Point number 1. There's something about subproblems might overlap. Might overlap. For example, that's something we'll see once we see the Java code for Fibonacci. In order for me to calculate Fibonacci of 6, for example, I need to compute maybe Fibonacci 4 more than one time. That's something we'll see. I'll draw the tree a little bit later. But in general, if you find that subproblems actually overlap in your recursive method, that means you may want to use dynamic programming. That's one sign. And when the subproblems overlap, that means you got lots of duplicate, lots of recomputation. You're wasting the resources over and over computing the same problem. Recomputation. For solutions to subproblems. Okay? And the consequence is, since you waste so much time at the runtime to really recompute, the running time can get very costly, very large, very costly running time. For example, exponential. I'm not saying for every recursive method it's going to be exponential. I'm just saying one example would be, it might just be exponential. And for example, the Fibonacci example we're going to see. We haven't seen that just yet, right? We'll see that. All right, that's the first idea. Whenever you're trying to think about subproblems for recursion, just remember subproblems themselves may not necessarily just disjoin from each other. They might overlap, right? In that case, you want to have a smart way not to compute more than once for the same subproblem. Okay, number 2. When we say we want to combine the solutions into smaller problems, this is saying, in order for me to get this solution to the original problem, I can simply get a solution here, get a solution here, get a solution here, and somehow combine them. For example, it can be plus, can be multiply, or can be adding them into a list, and etc. Somehow I have a way to combine them. Okay? If this is possible, we say that your problem has an optimal substructure. Okay, I'll write it down. So what we're saying is, when you go from solution for the subproblems to the solution to the original problem. So here we say that the problem that we are trying to solve has optimal substructure. What that means is, I'll try to maybe phrase differently. Number 1, the solution itself is compositional. The solution is composed of the solution to subproblems. Solution to is compositional. In order for me to get this solution, I can just compose different subproblem solution. Compositional, that's what I meant. Another way to say it, which you will see more in the literature, solution to the original problem. It can be built from solutions to subproblems. Of course, always remember, whenever we talk about subproblems, they got to be smaller. Otherwise, you got infinite recursion. All right, let me highlight the keywords. So one is about subproblems might overlap. And also, the problem has optimal substructure. So these two are just my first exposure to you, just about how these two criteria you should really pay attention to if you want to judge if a particular recursive problem should be converted into dynamic programming. Sometimes it may be, sometimes it may not be, right? Depends. Okay? I think at least we can do a little bit of Fibonacci, a little bit, but I'll show you the dynamic programming solution next class will be Wednesday. I'm going to go to the Fibonacci in one moment, but for those of you who might be interested, dynamic programming is not something you will put on the paper. It's definitely something you can program, right? I'll show you where you can find it. Just go to the lecture site. You will see that under the code, dynamic programming. So far, the Fibonacci sequence example that we're doing, just go there. You will see that I gave you 3 versions of the solution. One will be the regular recursion, which will be exponential. Second one will be the dynamic programming using top-down approach. Number 3 will be dynamic programming using the bottom-up approach. All 3, they all pass the JUnit test cases. I would suggest take a look at them also before Wednesday, before we dive into them. Right? The pattern for every dynamic programming problem you will solve will be similar, but not exactly the same. So you will see definitely something put into working. Okay. Okay, let's look at Fibonacci quickly. All right, so that's the sequence, right? I'm pretty sure you have seen that before. Let me assume that. Okay, it's called Fibonacci sequence, and the first 2 are considered the base cases, and the rest will be following some pattern, which can be defined recursively. All right. So here we say that the first two are the recursive base cases, these two. And let me define something called index for the sequence, which we're going to use also in the formulation. So let me call the index pretty much like an array. So index, we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we got 11 numbers in the sequence, but Fibonacci sequence is infinite. Okay? We're only looking at partially. Okay, index. So you can think about here, 0 is F0. Capital F standing for Fibonacci. 0 is the index. And also here we got F1, F2, F3, F4, F5, 6, 7, 8, 9, 10, and so on. And usually the method you got to define is give me an index. For example, I'll give you 100. What's the corresponding number in the Fibonacci sequence, right? Something like that. Okay. Let me say a bit more. And then we also got, for example, here, and beyond the base cases, beyond the first two numbers, you can see that here, 8, which is F6, is going to be the sum of the previous two numbers, which will be 3 plus 5. Oh, sorry, beg your pardon. 3 plus 5. F4 plus F5. Right, just one example, right? The pattern is going to go on. Okay? Right? Recurrence relation is the recursive definition in which for which we can just convert into Java code. I'm pretty sure you guys have done this in the previous course. Let's just get to it directly, right? If you're really struggling to see the pattern in the Fibonacci, please let me know. I can help you with that. Okay, so let's see. So what we have is F is a Fibonacci sequence, and then I'm trying to give some index I. And here the I is what we call a state, okay, about the state of the problem, which can be something very small or something very large, okay? The I here is corresponding to the index that we just denoted. Okay? Let me draw the correspondence to you, and we say that the I here is the state of the problem. Okay? You will see the state term in the slides. And then think about f of I is the original problem. I want to find out the ith number. Ith number in the Fibonacci sequence. And by definition, using a recursive definition, we got two base cases. Could be either 0 or 1. 0 for F0, 1 for F1. If I is 0, I is 1. And for recursive case, given that I want to calculate I, for example, I could be 6, in which case I need to get to I minus 1, I minus 2, right? You're just going to apply. So you'll be f of I minus 1 plus f of I minus 2. Let me just align them better. Oh, sorry, let me not bother. Okay. So here it would be if I strictly larger than 1. Okay. So what we have here is 0 and 1 here are the base cases. And then these two, this one here and this one here, these are the subproblems. This problem here, compared with the original problem, is strictly smaller. This problem here, compared with the original problem I versus I minus 2, this subproblem here is also strictly smaller. So we are trying to solve, in order to solve this, we can solve these two instead. That's a recursive definition. Okay. Let's also annotate them. So all the terms I'm trying to maybe brush up, since you may have heard about these terms. So these terms are all critical whenever you want to discuss dynamic programming, where you want to get the initial recursive solution that may not be efficient. So this will be subproblem number 1. This will be subproblem number 2. But they're subproblems. They are subproblems. Okay, of course, you can see the correspondence. So we got 0 and 1, the base cases in the Java code. And also, we got the 2 recursive call. The first recursive call for the first subproblem. The second recursive call for the second subproblem, right? Okay, I'll let you see the Java code, right? It's rather straightforward. I don't need to waste your time in the class. Let's now do something 2 minutes, okay? Let's say I want to compute Fibonacci 5. Let's not use the call stack to trace. That'll be too tedious, okay? This, we don't need to. Let's now try to draw the recursion tree and see how that's going to work, okay? We start with Fibonacci 5 right here. And then we're going to see, we'll eventually get to the leaves for the tree that will be corresponding to base cases. And then we have branches corresponding to the recursive call. That's the principle. Okay, let's do this one here, and then we're done. Okay, bear with me, because I really want to make a point about repetition. Okay, watch out here. So we got Fibonacci 5 to start with, which we know by definition is going to require to compute Fibonacci 4. And then once it is done, we're going to compute Fibonacci 3. Agree? So now we don't have to touch this until this branch is done. So let's now worry about this branch. Okay? In order to calculate Fibonacci 4, by definition, it's not base case. We still got to calculate Fibonacci 3 and then Fibonacci 2. And we're going to focus on this first. Once this is done, we can get to here. Right? Isn't this corresponding to something we have seen? Pre-order traversal, one thing. Also depth first search. Similar, not exactly the same. Okay, you can think about it why. Bear with me. Okay, and then we're going to go for Fibonacci 3. By definition, is going to be Fibonacci 2, and then Fibonacci 1. And then I'm going to do this one first. Almost there. Fibonacci 1, Fibonacci 0. Okay? So now, Fibonacci 2 is something we already solved. So we're basically duplicating the resources like a computation. You can think about what's going to happen. There's something I will start with. You can think about, in order for me to finish this part here, I can simply copy this part here and then put it here. And then once this is done, for Fibonacci 3, it is something we also have done for this entire branch. And we're just going to repeat it exactly here as well. So the point is, for recursive method, in many cases, at the runtime from the tree, you can see that there are so many subtrees that simply overlap. They're simply duplicates. So that will be a very strong sign. You should really try to use dynamic programming, which we'll see. All right, thank you so much. I'll see you on Wednesday.